Okay, this video we are going to talk about Vsepr theory and how you can use Vsepr theory to start to predict the three-dimensional shape of your molecule. So, Vsepr stands for valence shell electron pair repulsion theory. So what this theory basically tells us is that electrons are going to repel each other. And that makes sense because they all have negative charges. And we've said multiple times through this unit that like charges repel each other. So all of my electrons are going to repel each other. So what we are going to find is that our shared pairs, or our shared multiple pairs, if we have double or triple bonds, are going to position themselves so that they're as far apart as possible from another set of shared pairs of electrons, okay? So we're not talking about the pair itself repelling each other. You'll see when you take first year university that we talk about like upspin and downspin, and that's why they don't repel each other. What we're talking about is if we had an atom, what's an easy one to draw? None of them are really the best to draw. But let's think about if we had CO2, because that's one that we do actually draw pretty often, right? We would put the C, we would have the O, we would have the O, and then we would say, okay, there's a shared pair here, or two shared pairs, and two shared pairs, right? And then obviously we have our lone pairs. But when we're discussing Vsepr, we're not interested in lone pairs unless they are on the central atom. So the reason for that is when we are discussing shape, we are going to find that this set of electrons and this set of electrons want to position themselves as far apart as possible. So this is where it's really hard because when we draw things, we draw them on a piece of paper, and a piece of paper is flat, so it is two-dimensional. But molecules are not flat, they're not two-dimensional. They occupy 3 dimensions of space. So you're going to see that as we start drawing our Vsepr shapes, we're going to have to be able to account for the fact that molecules have 3 dimensions of space. You're going to see we're also going to use the model kits quite a bit, and that's because it really helps us visualize something. And that's something that's challenging with bonding because we can't actually see this, right? We can't go to the lab and be like, ah, yes, I see what this molecule looks like. Now I see it. We can't do that. We can use the models to manipulate it and try to visualize it, but it is definitely a very different unit than the other units we have done in this course. So what we find is that this pair, or I guess 2 pairs, are going to repel this other 2 pairs. They want to position themselves so that they're as far apart as they possibly can. They don't want to be smushed together, which is why I've drawn an O on each side instead of one up here and one down here, because then they would be really close together, even though there was an option to put them further apart, okay? So what we're going to find is that as we start to draw things, we always want to maximize the spacing between all the different pairs of electrons that we have around that central atom. We never want to mush everything together. We want to space it out nicely because that's what those electrons are going to do. They're going to repel each other, and they're going to move as far away from each other as they possibly can. So, shape-wise, I want to say 5 shapes that you need to know for Chemistry 20. There are more than 5 shapes, so if you start looking stuff up online, you're definitely going to find more than 5, but we're really only concerned with 5. So the first shape that we discuss is linear. Okay, we consider something to be linear because it basically looks like a straight line when we put it all together. So what we find for linear is that we have a central atom, which is going to be this, with 2 electron groups. Okay, it's obviously going to have 2 things attached to it. They want to repel each other as far apart as possible. The way to do that is to go to 180 degrees so that it allows them to be like this. So there's a lot of space this way, there's a lot of space coming forward, there's a 180 on the back side, and there's also 180 across the top, right? We have to make sure that we're considering the 3 dimensions of space. So how you're going to know that you have linear? You are going to have a central atom with 2 things attached and no lone pairs, right? If I look at CO2, I have a central atom, there's 2 oxygens attached to it, and there are no lone pairs on that carbon. That's why it's linear. Another example is HCN. Although it's a single and a triple bond, there's still going to be that central atom with two things attached and no lone pairs. So anytime you see that you have a central atom, two things attached, and no lone pairs on that central atom, it's always going to wind up being a linear shape. So am I going to sit there with an angle measure and measure your angles? No. But you know how to draw something straight. It should look straight. It shouldn't look all like bent and wonky and out of shape, okay? So linear is our first shape. Our second shape is what we call trigonal planar. So when we have trigonal planar, what this name tells us is trigonal, so kind of like a triangle, and planar, meaning it's flat or it's all within the same plane. So when we have trigonal planar, we have a central atom with three things attached to it and no lone pairs. You are going to find that they're all going to space out by 120 degrees, okay? And yeah, they're all going to be a central atom with three things attached. Most common example that we use a lot of the times is a boron something, like a BCl3. And that's because if you think of boron, it's our exception, right? Boron only wants 6 electrons. So if I were to draw my dot diagram for it, we would put B, we would have a Cl, we would have a Cl. Sorry, it's kind of hard to draw on the trackpad. And then we would have a pair of electrons, a pair of electrons, and a pair of electrons, right? Boron only wants 6. It has 6 right there. We would obviously also, if we were doing our dot diagram, all of these other ones going on with the chlorine. But when we are considering Vsepr, we're really only interested in our central atom. So because our central atom has no lone pairs, right? There's no pair here, here, or here that isn't attached to something, and it has three things attached to it, it is going to take on that trigonal planar shape. So if I were trying to draw this, in its Vsepr shape, we would have our B going straight up. We would have our chlorine coming down into one side would be another. And then in that third position would be the last one, right? So again, I'm not measuring with an angle, but it should be around 120, right? Biggest issue you guys tend to have, and mine maybe isn't perfect, this chlorine should probably be a little more angled this way, is just making sure that you don't make this 180. And sometimes I see you guys do that, and you'll be like, here's my boron. It's an awful B, but let's pretend that's a B. And then you put a chlorine up here, and then you put one here. And then you throw the last one in like this. Okay, this is not trigonal planar, right? This is 180 and these are 90. We don't want that. We want them to be about 120, right? So we're not looking at a T or a sideways T. We want more of this trigonal type shape, okay? All right, so central atom, three things attached, no lone pairs, is going to be trigonal planar. So our next shape is bent. You'll sometimes see it also referred to as V-shaped. I want to say sometimes it's also written as angular. We usually just call it bent. So this is a subset of trigonal planar. And why that is basically we've just taken away that bonded atom that was up here and we've replaced it with a lone pair. So your general set to something that is bent is going to be two things attached with a lone pair. Okay, this is why it's really important to draw the lone pairs that are on your central atoms. Because if you don't, you're going to look at this and you're going to draw it linear, but it's not linear. Because this pair of electrons, that lone pair, is going to repel these other two sets of electrons that are in this bond and in this bond. So angle's a little bit less. You don't really need to know why it's less. We're not going to, again, measure it with an angle. We're not going to ask you what are the numbers. It's just less because this lone pair that's sitting on the sulfur is always sitting here. It's never being shared to another atom. So because it's always here, it has a slightly stronger repulsion to this shared pair which is why they get condensed together a little bit more, okay? So my molecule is going to be bent when my central atom has one lone pair and two non-central atoms attached to it. So far everything is different, right? Linear, we had no lone pair in the central and two things attached. Then we had trigonal planar, where we had three things attached and no lone pairs. Now we're at bent, where we have two things attached and one lone pairs. So there is absolutely a memorization piece to this. You have to memorize what kind of orientation you have around that central atom so that you know what type of shape to draw, okay? So you're going to see that as we go through the next few shapes, they all have different things happening around the central atom. So we're really concerned with what is around the central atom. So far, all of the molecules we've drawn have been planar or flat. They all exist within the same plane. We don't have to do anything fancy in our diagram. But now we're about to start getting into molecules that do actually occupy 3 dimensions of space. So we're going to have to be able to illustrate that in our diagrams. Okay, and this is where in class we're going to spend time using models to help us build these and see what they actually look like. And you'll see that that definitely helps you visualize what it looks like. But what you're going to see is we now have kind of 3 different types of lines that we're going to use. We're going to use our regular straight lines like that to show that something is within the same plane. We are going to use wedges to show that something is coming towards us. And we are going to use dashed lines to show that something is going away from us. So when we get into these 3D models, it's really hard to visualize it without actually seeing it. So at school, we'll definitely have the model kits. You'll be able to see it and you'll be able to visualize it. Right now in isolation, I obviously don't have a model kit. So I just went into my children's Halloween candy and stole some Starburst to make a little model to kind of show you what this is going to look like when we get into some of our 3-dimensional shapes. So when we were talking about some of our previous structures, we described those as planar, right? So one of the structures we looked at was linear. So linear, as best I can with my awesome model, that's not very awesome because obviously they're kind of heavy. They're all going to go into that straight line. So it's a flat molecule, right? I can turn it like this and it's going to be flat. And I can turn it the other way and it's going to be flat. And then we looked at, what did we look at next? The trigonal planar. So we kind of have that more triangle type shape going on. Not that this is the best because, you know, square-sided candy doesn't always do 3D shapes great. So we have that, and it's considered planar because if I rotate it this way, they all line up. They're all in the same plane. Or if I lay them flat on my hand, they're all touching the surface of my hand. There's nothing kind of going all over. And the same thing was true when we went to the bent option, right? It's bent, but it's still, when we rotate it this way, all within that same plane. It's flat, right? I can touch it to my hand and they all are flat on my hand. Sorry, I'm trying to show this and not show just my fingers. So now we're going to start to get into 3-dimensional shapes. So what we're going to find is when we build them, they are not going to do that. They're going to have different shapes happening. And that's where we're going to use the straight line. So the straight line that we have here means that it's within the same plane, right? So if I had these two and only these two, I could use a straight line for this because they are within the same plane. But when we start to get in to some of our more complicated molecules, and as I start to build the next one, you're going to see that that doesn't hold true anymore. So, oh, I just broke my toothpick. Okay, but we look at this one, and this is our next shape. This is tetrahedral, and that doesn't happen anymore, right? If I put them on my hand, well, these two are sticking up. If I rotate it this way, I still have Oh my gosh, I can't see anything. I still have stuff sticking up. So I'm never going to be able to draw this molecule all with straight lines because there's stuff going up, there's stuff going in front, there's stuff going behind. So what we generally do with these molecules is we have to decide where the plane is going to be. So usually the easiest way to do that is just to hold your hand up and hold your molecule next to it and be like, how many things can I get to line up with my hand? So the way my hand is, and I know this is hard to see just based off where my camera is and how my arms are, but I can get this one, and this one to all line up with my hand. But then this one and this one don't. So because I can get these three to line up with my hand, right, and I'll rotate it more this way, so it's this pink one, and this yellow one, I would draw those with regular lines. So I gotta be careful where I put this, or my dog's gonna eat my super high-tech model. So if we have our central atom, I'll just draw a circle for it. We had the one that was sticking straight up, and it was in the same plane because when I held it next to my hand, it lined up with my hand. Then we had this one that's kind of coming down to the side, but it also lined up with my hand. So it also gets a normal line. But now we have this one. So this one, when I hold my hand up, it's coming towards you, right? It's not lining up with my hand like those other three are. So because it's coming towards you, we are going to draw it as a wedge. And I'm wedging it down because it does actually come down. Then we've got the last guy kind of back here. And when I hold my hand up, again, kind of hard to see on the camera, but you'll see in class, it's coming backwards towards, like, sorry, I'm doing this with respect to you. So it is going away from you, but towards me. So I'm going to draw that one as wedges. Okay, so generally what you're going to find with tetrahedral, which is what this shape is called, we get two normal lines. We get one wedge because it's coming towards you, and one of dashed because it's going away from you. If you are at home in quarantine while this is happening, if you have like little marshmallows, they might work a little better than Skittles, or not Skittles, Starburst. Skittles will not work so well. I don't think you'll be able to shove toothpicks into them. But some type of manipulative definitely does help make this a little bit easier to recognize, okay? So we have three-dimensional shape with this particular molecule. What we find is our angle changes to just under 110 degrees. Again, you don't need to actually know the number, but you need to be able to recognize that when we have a central atom with four things attached to it and no lone pairs, it's going to take on this tetrahedral shape, which is going to have two regular lines, one wedge, and one set of dashes, right? So down here, you have CH4. This one probably isn't the best because it has one coming towards you, two going away from you. I would suggest kind of ignoring that option and just sticking with this one. So two in the same plane, one coming towards you and one going away from you. So the one thing you're going to find is the more of these you draw and the more of these you build, you can definitely rotate the molecule and it's going to look different. You're going to draw it differently. But what tends to happen is if every time you draw it differently, then you don't start to see the pattern. So I would really suggest that once you identify the shape, try to always draw the same shape the same way so that you see that repetition piece and you're not sitting there eventually on a quiz or a unit test when you don't have a model kit being like, I have no clue what this looks like because I don't actually have it in front of me. Whereas if you've drawn it enough times and you've always drawn it the same way, then it starts to be, oh wait, that's this shape. I know that every time I drew it this particular way, okay? So next shape is pyramidal. So this is a subset of tetrahedral. What basically happens in this one is we take that top non-central atom off and we replace it with a lone pair. So we call it pyramidal. Again, kind of ignore that picture. We call it pyramidal because it kind of looks like a pyramid, right? So if I had my N, I would have one in the same plane coming over here, and then I would have one coming out, and then I would have the one going away. So if you compare this shape to what we drew for tetrahedral. The difference is simply that I don't have that one coming straight off the top. Instead, what we have is our lone pair sitting there, okay? So this is a pyramidal. It's going to have a three-sided pyramid. We're going to have that lone pair. Again, I can try to build this for you with my super awesome Starburst candies. So we'll have this as our, actually maybe I'll make this then, just because it's different color than all the other ones I have. And then we are going to have all of those H's coming into play. And they are going to be in this orientation. Sorry, you can't actually see what I'm building. And I broke my toothpick. Oh, totally broke my toothpick. Hold on. Whoa. Have to make sure I don't eat that when this is done because it has a piece of broken toothpick in it. Let me actually replace it for a full-size one. Okay, so we are going to wind up with this type of shape where we have our central atom, right? So why we had to do that is if I put my hand here, I can get this pink one and the yellow one to line up with my hand. But this guy here is sticking out towards you, hence the wedge. And this guy back here is coming away from you because it's behind the hand, hence the dashed lines that it's going to get. All right, last shape is actually a shape you've already done. The only difference with this bent is it's a subset of tetrahedral instead of a subset of trigonal planar. So we're going to take one of these away. We're going to go back to this bent shape. The difference now is we have two lone pairs instead of just one, okay? So angle-wise, it does result in a smaller angle than the other bent shape, but that really doesn't matter. You're still going to draw it as a bent shape, okay? So you want to be able to make sure that you're able to recognize what type or what shape you have based off of what you have around the central atom. So you are still going to find that a lot of the times with the Vsepr stuff, you still need to draw your Lewis dot diagram because you need to be able to look at it and figure out what do I actually have going on around my central atom and what shape does that mean. Once I've decided what shape it means, then I can actually go about drawing that three-dimensional shape. Again, it's going to take some practice to make sure that I can recognize what shape it is and that I know straight lines, wedges, dashes, what does it look like? So to summarize those shapes. So to summarize that, oh, that was not the button I meant to press. Hold on. We need to be able to recognize what shape we have based off of what we have around the central atom. So the first shape we talked about was linear. We said it was going to be linear when we have a central atom with no lone pairs and two non-centrals attached. Okay, the next shape we looked at was trigonal planar. We said it was going to be trigonal planar when we had a central atom with no lone pairs and three non-centrals attached. Then we looked at our first bent, right? So we had a central atom with one lone pair and two non-centrals attached, right? So all of these were all drawn with regular lines. We didn't have any type of three-dimensional shape associated with it. Then we hit tetrahedral, right? So we had a central atom with no lone pairs and four non-centrals attached. Then we went to our first subset of tetrahedral, which was pyramidal. And we saw that in pyramidal, we had a central atom with one lone pair and three non-centrals attached. Then we looked at our last shape, which was our second bent shape, right? So the only difference between this bent shape and the previous bent shape is that we have a central atom with 2 lone pairs and 2 non-centrals attached. So the only ones that we actually have to do any type of 3-dimensional shapes with are the pyramidal and the tetrahedral, right? These are the 2 that actually require that 3D shape. The other ones are all flat. They don't require any type of special wedges and dashes. They all just get normal lines. So because this is memorization, I do usually suggest for some of you, especially if you know memorization isn't your strong suit, make yourself some flashcards. It does definitely help. Even sometimes just the act of making them and writing it all down and summarizing it can be super helpful. But they are nice to have as you're studying, right? Because you have quizzes, you have unit tests, final exams. So those are nice to have when you're studying to make sure that you can kind of remember what they are and what you're looking for. So here are the steps that you want to take when you actually are drawing a 3-dimensional or Vsepr shape. So first thing we want to do is we want to draw our electron dot diagram or our Lewis diagram. And that's because we need to know what we have around our central atom or central atoms if we have more than one. So we have to make sure that we have the correct number of electrons and we're not adding things in that aren't actually there. Once we have that dot diagram, we're then going to look at what's around the central atom, right? How many non-centrals? Do we have lone pairs? From there, we can decide what shape it should be, and then we can actually draw the shape. So again, in class, we're going to spend some time with the model kits. That's really going to help you become more comfortable. If you are at home, I would suggest trying to see if you can find something that you could use as manipulatives. I would suggest probably marshmallows over Starburst, because the Starburst get super sticky and they're also very heavy and tend to break your toothpicks. But yeah, at school we actually do have the model kits for you to use. It's more so just if you're at home. So let's look at some examples. So first one we have is carbon tetrachloride. So carbon tetrachloride is CCl4. So whichever way you found was the better way for you to do your Lewis diagrams, that is the method you should follow to start, right? So regardless of which method you're using, we still have to figure out our total number of valence electrons. So we have carbon at 4, and then we have 4 chlorines at 7. So our total valence electrons is 32. Right? If we wanted to give everything a full octet, we have a carbon and 4 chlorine, so we have 5 atoms. None of them are special ones. So 5 times 8 is 40. So that means we have 8 bonding electrons or 4 bonds. So what's going to go in the middle? We are going to put the carbon in the middle because the carbon has the most unpaired. We're going to put the chlorines all around it. Okay, we're going to start with that dot diagram, and then from there we're going to figure out our shape, okay? So we take this, just going to move some stuff around a little, make it a little more efficient on space. So dot-wise, we said 4 bonds, so 1, 2, 3, 4. I don't need to do any double or triple bonds because that does take care of filling all of those spaces with the number of bonds we need. We need to fill valence shells now. So each chlorine is going to need 6 more. Okay, the carbon doesn't need any more because it already has 8 around it, so we're going to leave it alone. Once we finish giving all those chlorines full valence shells, we want to make sure that it actually works. So we should have 32 dots, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Everything has a full valence shell. So now that I have my Lewis diagram, now I can go about determining the shape. So I'm going to look at my central atom because that's always what we're concerned with. It has 4 things attached to it, and it has no lone pairs. So when we think about our shapes, the shape that had no lone pairs and 4 non-centrals attached is going to be tetrahedral. So we need to draw a tetrahedral molecule. So if we think about what tetrahedral looks like, we have our central atom. We have the one going straight up within that same plane. We have the one coming down into the side. And then when we put our hand up, right, we would get these three atoms to line up, but the other two didn't, right? One was coming out towards you, so the wedge, and the other one was going away from you, so the dashed lines. Okay, so that is going to be our tetrahedral shape for our carbon tetrachloride. Okay, then we have BH3. So BH3, if I were to draw the dot diagram for that, I have boron, right? And remember, boron is an exception. It only wants a total of 6 valence electrons. And then we have our hydrogens, right? We have 3 of them. So we're going to put those all around the B. Right? If we figure out how many valence electrons, boron has 3. Each hydrogen has 1, so we have 6. Okay, if we wanted to give everything a full valence shell, each hydrogen wants 2, boron only wants 6. So that is 12, not 13, 12. And then we do 12 minus 6, which is 6. Then we divide by 2, which is 3. So we need 3 bonds. 1, 2, 3. Okay, you probably could have drawn this one without doing any of that and just kind of done it, but there's nothing wrong with doing all of that there to confirm that you've done this right. So we have 2, 4, 6 electrons. That matches what we were supposed to have. Every hydrogen has 2, which is what it should have. Boron has 6, which means it's also full. So shape-wise, we have a central atom with 3 things attached and no lone pairs. Appropriate shape for that is trigonal planar. Right? So definitely a memorization piece of I need to know that that orientation means that. So when I go to draw this, we're going to have our B. It's planar, so everything is within the same plane. Remember, it's trigonal. So there was the one coming straight up, one down here, one over here. And then obviously we got to put our actual H's in. Sorry, that's not a very good H. But let's just pretend it's a nice looking H. Okay, so that's my BH3. And then you just kind of keep going, right? So definitely practice. The more you practice, the easier this becomes. If you don't practice, then it's really hard to be able to piece this together, right? And this is also where you have to make sure that you're feeling pretty confident with your dot diagrams. Because if I do my dot diagram incorrectly, that is going to lead to me not drawing this final diagram correctly. So really important to make sure that you are practicing and making sure that you feel comfortable with drawing 3-dimensional shapes. Because either the next lesson or the one after, we're going to take this one step further. So really important to make sure that you can do the dot diagrams so that you can recognize what kind of shape it is so that you can actually draw that shape. Okay, I know I skipped a couple examples that were in your notes, but we're going to do this one here. And we're going to do this one because there's more than one central atom, okay? We have C2H2. So our configuration for that is going to be the 2 C's in the middle, each with an H. Okay, and definitely the more practice you do, the easier it becomes to recognize when you have more than one central atom. So how many valence electrons can we have? So we have 2 carbons that each have 4, and then we have 2 hydrogens that each have 1. So we are allowed to have 10 electrons in our diagram. If we wanted to give everything a full valence shell, we have 2 carbons wanting 8 and 2 hydrogens wanting 2. So we would need 20, which means we have 10 bonding electrons. So we need 5 bonds. So 1 bond, 2 bonds, 3 bonds. We need 5, so we need 2 more. I can't put it between the carbon and the hydrogen because hydrogen's full valence is 2 and it already has that. And I can't put it here either because I also have a hydrogen, so it's already full. So I'm going to have to put a triple bond here so that I have 1, 2, 3, 4, and 5 bonds, which is what my math told me I needed. So we have 2 central atoms. So when we are doing this, we have to look at this part to determine the shape around this central atom. Then we have to look at this central atom and determine what shape is around that. So if I look at this carbon, it has 2 things attached to it. It has the H and the C. It has no lone pairs. So that means it's going to be linear. So we're going to have the H to the C to the C, and they're all going to be in a straight line. So this is a single bond, right? Because we just had the 1. And this here is going to be a triple bond because we had the triple bonds. Now we're going to go to this one. We need to throw that H in. We need to figure out where it's going to go. So when I look at this carbon, also attached to 2 things, also has no lone pairs. So because of that, it is also going to have a linear shape around it. So we have 2 shapes in this molecule, right? We have a shape around this carbon, and we have another shape around this carbon. In this case, it just so happens that they both have the same shape, which is going to be linear, okay? Not always going to be true. Sometimes you're going to find some that have some different shapes. So let's just change this here. We'll look at one like that. So maybe let's look at CH3OH, okay? So in CH3OH, we're going to have a C. It's not moving. It's frozen. Okay. We have a C with 3 H's, right? We have our central atom. What's on it? So the C is the central, the 3 H's. Then we have our next central, which is the O. And then what's on that? Which is the H. Okay, so CH3OH. You're going to find generally when the formula is written this way, it's always going to go central atom, what's on it? Next central atom, what's on that? So when we look at it, we start to do our math. So carbon has 4. We have 4 hydrogens that each have 1. And then we have oxygen, which has 6. So we have a total of 14 valence electrons that we can have in our diagram. So if I wanted to give everything a full valence, this carbon wants 8. I have 4 hydrogens wanting 2, and then I have an oxygen also wanting 8. So I get 24. So 10 bonding electrons, 5 bonds. So going back to our diagram, 1 bond, 2 bonds, 3 bonds, 4 bonds, 5 bonds, right? We have now filled all of those locations. So don't need to put any double bonds or triple bonds in because we needed 5. We have 5. So this hydrogen has a full valence. So does this. So does this. This carbon already has 8, so it's good. Oxygen here has 4. So 6, 8. This hydrogen is also already full, so we don't have to worry about that. So we should have 14 dots. 2, 4, 6, 8, 10, 12, 14. We do. Everything has a full valence shell. So now we need to look at these. We have 2 central atoms. They're going to have different shapes around them. That makes sense because this carbon has 1, 2, 3, 4 things attached and no lone pairs. The oxygen is my other central. It has 2 things attached and 2 lone pairs, so not the same shape. So if we start with the carbon, it has 4 things attached and no lone pairs, so that means we need to do a tetrahedral shape. So one thing we want to make sure of when we do these types of diagrams where we have more than one central, always make sure that your centrals stay within the same plane. So if you think about when we draw a tetrahedral, we always get 2 within the same plane. So I'm going to make these 2 be within the same plane so that both of my central atoms look normal. But then we have to have a wedge and our dash. And we're going to have our hydrogens off of these. Okay, so there's my tetrahedral shape around this carbon. Now I look at my oxygen. It had two things attached to it and two lone pairs. So the appropriate shape when we have two things attached and two lone pairs is bent. So I already have the one line. Either I could put the other one here or I could put it down here. It really doesn't matter. I'm going to put it over here just because space-wise I have more space over there. So my H is going to go here. And then I'm going to have my two lone pairs. So I have two different shapes, right? Around this guy here, we have our tetrahedral. But then around this one, we have bent. Okay, so possible to have more than one shape in a molecule when we have more than one central atom. You are going to get questions like this. Again, you are going to get some time in class to practice with the models. It does tend to help really make it a lot easier to visualize what it looks like. But really important to practice the Vsepr stuff. It's definitely theory-wise some of the harder stuff that we do in Chem 20 because you kind of have to close your eyes and be able to picture what this looks like. And if I told you to do that right now, you'd probably look at me like I was crazy and be like, that's not going to happen, Miss Chip. Like, I can't close my eyes and picture some magical three-dimensional molecule with wedges and dashes and dots. But the more you practice, the easier it becomes, and you'll start to see that it really isn't as bad as it seems. But if you don't practice it, then it is as bad as it seems. Okay, so really important practice. You're going to spend some time with the models. You're going to spend some time working through a bunch of examples on Vsepr in your booklet. You'll see that I think there's like 5 pages or something like that. And it's because it is a really important concept.